Welcome. In this lecture, we'll be talking about transaction processing. To achieve better performance and faster response, systems allow multiple users to access and to update data simultaneously. The concept should not be something foreign to you. A similar idea applies to highways, which allow vehicles to travel in both directions at the same time and provide multiple lanes to increase the traffic flow. In a transaction processing system, we have a database and concurrent users executing database transactions. One concern we have when multiple users come into play is that such a system has to take great care to avoid what we'll call inconsistent data. This would be data that violates business rules for the application domain. For example, consider an airline reservation system where many potential travelers are looking to book a seat on a flight to some exciting or exotic destination. There must be some control over the way these potential travelers are allowed to book a seat. Clearly, we don't want passengers sitting on the laps of other passengers. To ensure that at most there is a single passenger assigned to a single seat, some form of concurrency control must be in place. This control defines a set of behavioral rules and ensures a predictable outcome. Now, in a transaction processing system, obviously we're processing transactions. So that raises the question, what is a transaction? Well, a transaction could be thought of in a simple, somewhat general sense as being a collection of operations that performs a single logical function as part of a database application. We'll have much more to say about this in the video. So let's get started. We indicated that a database management system allows multiple users to access persistent data at the same time. Let's discuss a few of the key concepts related to transaction processing. Because a DBMS allows multiple users to access persistent data, inevitably, some users will wish to access the same data at the same time. So a DBMS must provide some kind of control to prevent users from interfering with each other. This is referred to as concurrency control. There are different approaches that some systems have taken, but the idea of concurrency control in general addresses how to deal with access to shared resources. The controls used in a database management system provide a predictable behavior when users attempt to access the same data at the same time. These controls are like the use of traffic lights in a downtown intersection. Assuming that drivers abide by the rules of the road, there will be no incidents of two vehicles passing through the intersection and colliding. In the database, we avoid the possibility of inconsistent data resulting from concurrent updates by establishing and abiding a similar set of rules. Transaction management is another key concept. This deals with the way modifications to the database are going to be accomplished. In an earlier video, we compared a database to a filing cabinet. We noted that in addition to storing data, we might also need to update previously stored data. With respect to concurrency control, we need to consider that two users might wish to change the same data at the same time. A DBMS, then, must ensure that concurrent requests for data retrieval and data update are conducted in a predictable manner. This is one of the key points we will address in this video. Additionally, techniques to prevent multi-user interference also contribute to database recovery. We'll consider this topic in a separate video. A transaction is referred to as a logical unit of work, or an LUW. What is meant by logical? Well, a transaction consists of a set of application-specified operations applied to the database. It's common for a transaction to involve multiple operations. Consider, for example, the transfer of funds from a savings account to a checking account. There are actually updates to the savings account and to the checking account, and perhaps an additional record being inserted into some kind of a transaction log or activity log. But the operations that comprise a transaction may consist of the entire program, or only a portion of a program, or it could simply be a single operation executed from within the program. A transaction has a property of being all or nothing. If it is not possible to complete all operations in a transaction, then we don't want to complete any of them. None of them will be allowed. Consider the banking transaction previously mentioned. If it was possible only to decrease the balance of your savings account, but we could not increase the balance of your checking account to complete the transfer, it's unlikely that you would want to do just that single operation. Another important point about a transaction is that although a transaction is most often considered in the context of data modification, there is also a concept of what is called a read-only transaction. In such a transaction, no changes are applied to the database itself. However, we might need to view a set of data at some point in time to get this consistent view of the data. Consider long ago in a galaxy far away, where at one time it was necessary to actually physically visit a bank to make a deposit or a withdrawal. The bank opened its doors to customers at 9 a.m. and closed them promptly at 3 p.m. If you failed to arrive within that time period, you would need to return the following day to conduct your business. So what does this have to do with a read-only transaction? Well, that's a good question. Suppose that we wished to view all account balances as they existed at the end of a business day, that is, at 3 o'clock, when the bank closed its doors. In the era we just described, we actually had the luxury of viewing these balances anytime from 3 p.m. until just prior to 9 a.m. the next business day, because no additional activity would be conducted. The balances would remain unchanged. Well, someone came up with the idea of an ATM, which allowed customers to update accounts at any time of the day. How could end-of-day business balances be determined if activities continued beyond 3 p.m.? Another really good question. It would be necessary to freeze the view of account balances for a user who is performing the summary for end-of-day balances, yet allow another user, the bank customer, to make deposits and withdrawals. So what is needed is a way to isolate the actions of one user from those of another. This isolation property of a transaction ensures that each transaction appears to execute in isolation from other transactions, even though the transactions are executing concurrently. A transaction should always bring the database from one consistent state to another. Consistency is related to business rules. If an update to the database results in data that does not conform to the business rules captured within the database, that data is inconsistent. Allowing inconsistent data to exist within the database would mean that the database no longer models or reflects the character of the real world. Thus, inconsistent data is not allowed in a database. Because a transaction may involve a group of operations, it is possible that the results of any single operation will produce some inconsistency. Concurrency control mechanisms ensure that such inconsistent data is never exposed outside of the transaction. Upon completion of all operations within the transaction, the database should achieve another consistent state. Now, consistency refers to data conforming to a set of application-defined or application domain-defined rules, which can be enforced through application code, through declarative constraints defined to the database system itself, or through procedural integrity. Other than application code, this would entail something like a database trigger. So a transaction might be either simple or complex. Consider the two tables in the academic database called course and class. A simple transaction might entail changing the lab fee, the C lab fee value in the course table for some particular course. This could be accomplished with a simple data manipulation statement. Update the course table, set the lab fee to its new value for the targeted course. This change involves exactly one row in a single table. It will not affect rows in other tables. An example of a complex transaction might be something like changing the course number value for a course. C&O resides both in the course table and in the class table, which is related to course. So a change to the C&O value would be required in both tables. So this is a more involved transaction because the related records in class must also be updated, because class C&O is a foreign key that references the C&O column in the course table. If these records in the class table are not updated, the database will be in an inconsistent state. We'll have classes referring to a course that no longer exists. So referential integrity in commercial products implements a delete rule. This can be specified when the tables are created. But the situation to which we're referring now is not a deletion, but an update. The update rule from relational theory is not fully supported in most commercial products. The update rule is implicitly defined as restrict, and that means it disallows any change to the primary key when a row with a matching foreign key exists. So we need to understand the boundaries between transactions. That is, when does one transaction end and another transaction begin? When a transaction begins, data in the database is in a consistent state. This means that all data conforms to the business rules reflected in the database. When a transaction ends, we must have arrived at another consistent state. At the end of a transaction, it would be reasonable to expose the data that we were processing to another transaction. However, within the individual operations of a transaction, data may temporarily be in an inconsistent state. Hence, it would be inappropriate to expose such data to users or to other transactions. So during the execution of the operations that comprise a transaction, the database may temporarily pass through an inconsistent state, and the changes made during a transaction should not be available to other users or programs operating on the database until that transaction has signaled its successful completion. In general, users and programs must only see consistent data. The concept of what is called a sync point or a synchronization point is the boundary between two consecutive transactions. All transactions begin and end at a sync point. At a sync point, the data are said to be synchronized. They conform to business rules. So at a sync point, the database is in a consistent state. When a transaction completes, the database must be in a consistent state. So the changes made during a transaction are going to be either made permanent in the database, hence becoming visible or exposed to other users and programs, or must be undone and the database reverts to the previous sync point or consistent state which existed at the start of the transaction. With a successful transaction, we've made changes and we wish for these changes to be made permanent within a database. So a successful completion of a transaction results in these changes being committed. They become available to others within the system. An unsuccessful completion of a transaction would mean that we were not able to complete all of the operations satisfactorily. Therefore, we want to refer back to the state that existed at the beginning of the transaction and reestablish that. So we will undo or roll back any of the changes made during the transaction. It's as if the changes were never made in the first place. So a committed transaction cannot be undone. If we wished to remove the changes made by a transaction that has been committed, it would be necessary to create a new transaction to remove those changes. Within the logic of an application, it is the programmer who wrote the code that is generally responsible for determining the beginning and the end of a transaction. Some database systems support the concept of an explicit begin transaction and an explicit end transaction type of statement. Microsoft SQL Server supports begin transaction to initiate explicit transactions. With an explicit transaction, an application can perform a group of operations, and then the application decides what is to become of these operations. What is the fate of the operations? If an explicit transaction is not initiated, then on such a system, a transaction is considered to consist of exactly one operation or a single SQL statement. For example, two successive update statements that have been executed within an application would be considered two distinct transactions. This is due to something called an automatic commit or an auto commit. We should note that if you're working with Oracle database using Oracle Live SQL, that this system also uses a similar type of auto commit. For a transaction that involves multiple statements or operations that we want to treat as a unit using Oracle Live SQL, it would be necessary to group these statements in a block of code to allow an explicit commit or rollback to be performed. And we'll demonstrate that a little bit later using a language called PLSQL to create such a block. Oracle database in general does not use begin transaction. In fact, normally Oracle database and DB2 would fall into a category where they consider the start of the program as the implicit start of a transaction. It just so happens that the environment made available to us with Oracle Live SQL is kind of not the DBMS so much that's controlling the transaction as it is the way the transaction has been established through the front-end tool, the Oracle Live SQL interface. So if a program succeeds then in modifying the database and then terminates without an error, and we have not explicitly indicated a commit or rollback of the transaction, then the system will automatically commit the changes. This is referred to as an implicit commit. The outcome of a transaction may be determined by the executing program. The program could say everything is fine and we want to make the changes permanent. This can be accomplished by issuing an SQL commit statement. This is an explicit commit. Alternatively, the program could detect some kind of a problem, such as a violation of a business rule, and abort the transaction. In this case, the program could issue an SQL rollback statement, and this would explicitly roll back or abort the transaction. So both commit and rollback are SQL statements and can be executed within an application. These operations serve to end the current transaction and establish a sync point. Note that these operations will only end the transaction. They will not terminate the program that issued these commands. When a sync point is established, all updates since the previous sync point are either made permanent if we issued a commit, or they're undone if a rollback was issued. All positioning is lost. What this means is that cursors used to process result sets are closed. And all transaction established locks, a concurrency control mechanism, will be released or removed. In general, a cursor is an internal work area used to process the set of rows for an SQL statement. A cursor is used in an application to bridge the gap between set-level processing of relational database in SQL and record-level processing inherent in most programming languages. One use of a cursor is to enable a set of records to be accessed one at a time. The concurrency control mechanism of a lock is commonly used to protect a resource from other users while that resource is being accessed. It's a mechanism to implement concurrency control. We'll talk a little bit more about this in just a bit. Let's use this graphic to illustrate the idea of a transaction. The transaction starts at one point on our timeline and progresses from left to right, as indicated by the arrowhead. Each dot that we show along the way represents an SQL data manipulation statement or the effect of such a statement, such as an insert, an update, a delete, causing some change to occur within a database. If we complete all 5 of these operations, the application might choose to say everything went well and I would like to apply these changes permanently to the database, and the application would issue a commit statement. Alternatively, anywhere along this line, after executing some number of these changes, the application might say, things aren't going so well. We've got a problem here. What we want to do is back out those changes that we have made, undo those changes, and the transaction may choose to issue a rollback statement, in which case the transaction will end and the database kind of reverts back to the state it was in at the start of the transaction. This does not affect other users. It affects only the changes to data made by this transaction. When multiple transactions are executing, there's a concern that one transaction will attempt to perform operations that could interfere with the operations of another transaction or application. So this interference can result in data inconsistency. There are 3 classic problems that are typically discussed when talking about transaction processing. 3 ways in which a transaction could produce the wrong answer as a result of interference. One is called the lost update, another is called inconsistent analysis, and the third is called an uncommitted dependency, also known as a dirty read. These are the 3 classic problems that arise in the context of concurrent access to data. Interference results from the interleaving of actions of 2 transactions. Updates of one user or program may potentially interfere with the reads or updates of another user program. So let's talk a bit more about interleaving. When a database executes transactions serially, that is, one at a time, the actions of one transaction are processed before the actions of the next transaction. The benefit to this approach would be consistency is guaranteed. However, it's not practical in a multi-user environment. If you have one very long-running transaction, everyone else would have to wait for that transaction to complete before the next one could even be started. So the interleaving of actions allows more users or programs to be serviced in a given time period, while also maintaining consistency. We should note that interleaving by itself does not always result in inconsistency. Let's consider two transactions, transaction A and transaction B, that are going to be executing in such a way that neither one will run entirely to completion before the other one starts. That is, we will not experience the true serial execution, but interleaving will occur. What happens is transaction A at time t1 will get a little slice of the CPU and execute and do a bit of its work. It will then be interrupted and suspended, at which time transaction B would be allowed to operate for some period of time. Again, B will be interrupted and suspended, and A will be resumed. A again will be interrupted and suspended, and B will resume, and A will resume, and so on. Here we show the complete idea of the interleaving of transactions A and B. Serial execution of transactions means that transactions are performed one after another without the interleaving we just described. Serializable means that the interleaved execution of transactions is managed in such a way that it produces the same result as some serial execution of the same transactions. Thus, we can make it look like it's serial execution, but have the benefit of interleaving. So achieving serializability is called transaction isolation. A database is said to be consistent if its state after the execution of a set of transactions is exactly the same as if those transactions had executed serially. So serializable concurrent transactions accessing shared data cannot interfere with one another. There are four properties of transactions that collectively form what is called the acid principle. The A comes from the transactions being atomic. Each transaction must be atomic, meaning that the actions are executed entirely or not at all. The C comes from consistency. Each transaction should bring the database from one consistent state to another. The I comes from isolation. Each individual transaction should be seen as being run in isolation. Interference from other transactions will be avoided. And finally, the D comes from durable. Each transaction should have persistence with respect to failures. The result of a transaction should survive even in the event of a future failure. With that background, let's talk about the motivation for concurrency. Given a correct state of the database as input, an individually correct transaction will produce a correct state of the database as output if executed in isolation. However, an independently correct transaction can result in an incorrect state within a database due to the interleaving of transactions. and this is due to that potential interference that we discussed. So what we need is some way to ensure that the correct results are produced by concurrently executing transactions. And what we need then is some form of concurrency control. We note that a transaction is also then a unit of concurrency. So we said a transaction is a unit of work, it's a unit of recovery, and it's also a unit of concurrency. Let's briefly examine those three problems that we described that contribute to the notion of interference between transactions. The first is the lost update problem. Suppose we have a record in the database R, or a row within some table in the database R, and it contains a field X. The value of X currently is 10 at the start of our transactions. So at time t1, transaction A says, I'm going to locate and fetch, I'm going to read record R. Then, due to interleaving, it is suspended and transaction B comes in. And transaction B likewise says, oh, I need to read record R. So they each have within their working storage an image of R that has a value of 10 in field X. Then at time 3, transaction A is resumed, and it chooses to update record R by changing the value in X to X plus 1. It increments the value of X. So it produces a value of 10 plus 1, or 11. Now remember, transaction B, when it resumes, has the same exact copy of record R that transaction A had been working with. So the version of the record that transaction B is working with shows a value of 10 in field X. The goal of transaction B was to double the value of X, multiply it by 2. Now the result is going to be 20. What happens is the update that was made by A was overwritten with the update that was made by B. So assuming that the transactions operate in isolation, the possible valid results from the executions of transaction A and B would be 22 for X if A completes before B starts, 21 if B completes before A starts. So without concurrency control, transaction A's update is lost as it is overwritten by the update made by transaction B. So we wish to avoid this kind of a problem. To avoid it, a concurrency control mechanism could, at time t2, prevent transaction B from finding and reading that record because someone else is already using it. At time t3, we could prevent transaction A's update because two different transactions have both read the record. At time t4, we could prevent transaction B's update. So there are different ways that we could accomplish the concurrency control and avoid this lost update problem. These first two methods that were described can be handled by a technique known as locking. Many commercial databases use a locking scheme for concurrency. We'll examine that in some detail. The third method could be achieved by using a technique of concurrency control called timestamping. The second problem is called the uncommitted dependency problem. This problem is associated with one transaction looking at data that has been modified but not committed. It's operating under a false assumption. So at time t1, transaction A performs an update of record R. Transaction B fetches the record, which reflects the update made by transaction A. And then transaction A said, oh, I really don't want to do that. So it rolls back and cancels its update, meaning that the actual record now in the database does not include the modification made by transaction A. However, the version of record R that B is looking at reflects that update, but that update is not in the database. So transaction B becomes dependent on an uncommitted change that occurred at time T2. A variation on the uncommitted dependency problem, or another form of this problem, involves the update of uncommitted data. Transaction A updates record R. Transaction B updates record R. And then transaction A says, oh, I'm backing out what I've done. In reality, it backs out all changes that have been made, the result being transaction B has made an update, and it updated an uncommitted change at time T2 and loses that update at time T3. And finally, the inconsistent analysis problem. If a transaction sees an inconsistent state of the database and performs operations based on what it sees, the transaction is performing what we refer to as inconsistent analysis. Assume that transaction A has the goal of summing the account balances, and transaction B has a goal of transferring an amount, say 10, from account 3 to account 1. The initial balances, when this whole scenario starts, is account 1 has a balance of 40, account 2 a balance of 50, and account 3 a balance of 10. Let's examine the problem in some detail, given this background. At time T1, transaction A fetches account 1, which has a balance of 40, and says, okay, the cumulative sum that I'm producing is, of course, 40. I've looked at only one record. It's allowed to do another fetch, and fetches account 2, value of 50, the sum is now 90. And then, due to interleaving, it's suspended, and transaction B kicks in and fetches account 3 with a balance of 30. It then modifies account 3, so the new balance becomes 20, and performs a similar update with account 1. Remember, the objective of this transaction was to effectively transfer a value of 10 from one account to another. So then it commits its change. Now transaction A gets a chance to resume, and when it reads account 3, it doesn't see the value of 30, it sees the value of 20. This is like that end of day account balance summary that we discussed earlier for a banking application. We're now seeing a value in account 3 that is not really consistent with respect to the time for with the values for account 1 and account 2. We wanted them all to be reflective of the same point in time. So account 3 is actually giving us a different value than we really should be working with if we say that we wish to see the sum of all account balances as they existed at one point in time, say 3 p.m. Well, that's as far as we'll go in this current video. Let's recap some of the key points of what we addressed. We came up with a definition of a transaction. Initially, we said it was a logical unit of work. As we discussed transactions in more detail, we said that these transactions have certain properties that adhere to what's called the ACID principle. We then discussed synchronization point, or sync point, and indicated there's a concept there of a consistent state of the database. Additionally, we talked about how transactions are completed within the system. We talked about implicit and explicit types of commits or rollbacks. But more precisely, we discussed with the explicit type of completion of a transaction that there were SQL commands or SQL commands for commit and rollback that could be executed within an application program. Additionally, we talked about how multiple transactions can be executing at the same time through a process called interleaving. And then we noted how interleaving can introduce potential problems with concurrent execution of transactions. So we discussed three classic problems. And then we identified a potential solution to these problems in the form of locking. We've kind of run out of time, so in our next video, we'll pick up at that point and discuss how locking can be used to solve the concurrency-related problems introduced by interleaving.